Welcome back once again. In previous lecture we had shortest job first scheduling algorithm and we had discussed the concept of this SJFS algorithm, and also we have seen how we can prepare the Gantt chart if it is primitive and non-primitive. We have one problem, and this problem means the question has been asked in GATE 2014. So I have taken this question from GATE 2014 question paper. An operating system uses shortest remaining time first scheduling algorithm for primitive scheduling. Now we are saying that means they have clearly mentioned a primitive scheduling of processes, means using the shortest remaining time first scheduling algorithm instead of shortest job first scheduling. They have mentioned shortest remaining time first scheduling algorithm for primitive scheduling of processes. So the processes has to execute in primitive fashion. So consider the set of processes with their arrival time. So we have arrival time also and the CPU burst time in milliseconds. So P1 arrival is 0 and burst time is 12 millisecond. P2 is arrival time is 2 millisecond and burst time is 4 millisecond. P3 arrival is 3 millisecond, burst time is 6 millisecond, and similarly P4 is arriving at 8 millisecond and its burst time is 5. So based on this we have to prepare the Gantt chart. So the Gantt chart has to prepare first and then we can calculate the waiting time, turnaround time, etc. Now they have asked us to prepare or to calculate the waiting time, right? So waiting time of the processes. So what would be the waiting time? So they have given the four options: 4.5 millisecond, 5 millisecond, 5.5 millisecond, and 6.5 millisecond. So we can't answer right now because we have to prepare the Gantt chart and then we have to calculate the waiting time of each process. Then only we can find the average waiting time of the processes and we can solve the question, right? So let us move and prepare the Gantt chart. So first prepare the Gantt chart with timeline. So this is the timeline. So Gantt chart is prepared. So P1 is arriving at 0 millisecond. So first we are allocating P1 at the 0th millisecond, right? And after 2 seconds one more process is arriving which is having a less CPU burst time than the P1. So we are having shortest job first scheduling algorithm, means we have to execute the P2, right? But it is arriving 2 minutes after 2 seconds, or we can say 2 milliseconds. So up to 2 millisecond P1 can execute, but after the 2 millisecond the P2 occupies the CPU till it completes its complete burst time, that is 4 millisecond. So it occupied at 2 millisecond, completes its burst time 4 millisecond, exit at 6th millisecond. Okay. So during the execution of P2, one more process is arriving at 3 millisecond. Means during the execution of P2, the third millisecond, so one more process P3 is arriving and it has 6 millisecond of CPU burst time. So till now, till 6 millisecond, right, we have not we don't have any fourth process right now. Only the two process executed, one more in pipeline, one more in a ready queue, that is P3. So now the P3 will get the CPU, right? And it will complete its burst time, right? So it will complete it burst, CPU burst time. So 6 plus burst time is 6, 6, 6, 12, right? So during 8th millisecond, assume that during the execution of P3, even though P4 arrives with 5 millisecond burst time, till that the P2 has already executed 2 millisecond. So total burst time is 6 milliseconds. 6 minus 2, 4 millisecond means the shortest one is the P3 compared to P4 at the 8th millisecond. So hence it is continuing till 12th millisecond. So after the 12th millisecond, so at the 12th millisecond, the P3 get exit from the CPU and the P4 is allocated CPU, right? So P4 will allocate the CPU and it completes its burst time, that is 5 millisecond from 12 to 17. At the 17th millisecond it will exit, right? And the P1 process which was waiting, so which was already completed 2 millisecond of execution, and it has 10 millisecond of burst time, right? It is waiting, so it will enter in 17th millisecond and completes it 10 millisecond of work or CPU burst work and exit at 27th millisecond. So this is how we can prepare the Gantt chart for this problem. So after preparing this Gantt chart, we have to remember this formula. So waiting time. So how to calculate the waiting time? So total waiting time of the process minus number of millisecond the process executed, right? So we have to calculate the total waiting time and number of millisecond process executed minus its arrival time. Okay, let's calculate it. There is a P1 process, right? So its total waiting time is 17 millisecond. Why? The P1 is executing for 2 millisecond here and the re-entry take place at 17th millisecond. So hence the total waiting time is 17 millisecond. Here it is not waiting, so zero waiting time, right? But till 17th millisecond it is waiting because another 10 millisecond CPU burst time is pending, right? So hence 17th millisecond is the total waiting time of P1 minus 2, that is the number of millisecond process executed already, that is 2 millisecond it is executed, right? Arrival time is 0, so 0, right? 17 minus 2 minus 0 is 15 millisecond is the waiting time of P1. Similarly, for P2 we can calculate the total waiting time, so that is it is arriving at 2 millisecond and it is immediately occupying the CPU. So its waiting time is 2, right? Waiting time is 2 minus number of millisecond process executed, that is 0, and arrival time is 2. So 2 minus 2, 0 millisecond. So the waiting time of P2 process is 0 millisecond. So at the second millisecond, 2 millisecond, when it arrives, immediately it is occupying the CPU, hence the P2 waiting time is 0. Coming to P3, right? So P3 means it is entering at 6 millisecond. It is waiting 0 to 6 millisecond, means total waiting time is 6 millisecond. Number of millisecond processed is 0, right? And the arrival time is 3 millisecond. So 6 minus 3 is 3 millisecond waiting time for P3. So it is just waiting for 3 millisecond. Okay. So arrival time is 3 millisecond. It arrived at this point. I have already mentioned. At this point, P3 has arrived, but it is waiting till 6 millisecond. Means 3 to 6, that is 6 minus 3 is 3 millisecond. So the duration of waiting of P3 is 3 millisecond. Now P4. So 12 is the total waiting time, right? So P4 is entering here at 12th millisecond minus 0. 0 is the number of millisecond process executed, that is 0, right? 8 is the arrival time, right? So 12 minus 8 is 4 millisecond. So it is waiting 4 millisecond because it is arriving at 8 millisecond and it is occupying CPU at 12th millisecond. So 8 to 12th it is waiting. So 8 to 12th means 4 millisecond it is waiting. So hence in this fashion we can calculate all the waiting times of these four processes. So after calculating all these waiting times of these four processes, then we can calculate the average waiting time by adding 15 plus 0 plus 3 plus 4, right? So we can calculate 15 plus 3 is 18, 18 plus 4 is 22, 22 is divided by 4, that is 5.5 millisecond is the average waiting time, right? So as per the GATE 2014 question, the 5.5 is the answer. So this question is asked in 2014 GATE examination. So as per this, they will give you the table. So first of all, you just understand that they will give you the table and arrival time. Based on that arrival time, you need to prepare the Gantt chart. So if you make the mistake while preparing the Gantt chart, your waiting time will be wrong and average waiting time calculated become wrong. So you must prepare a proper Gantt chart to get the answer. So 5.5 is the answer. So hope you understood this. So next lecture we will understand the round robin scheduling algorithm. So thank you for watching.